Okay, so the third part, the third component that we have to study, this is the combustion chamber. Combustion chamber, maybe you have had some classes on combustion in other classes, maybe combustion in internal combustion engines, maybe combustion of gases in burners in general. I have to say that we are in a rather different situation compared with internal combustion engine burning liquid fuels, or with regard to burners where you are burning a gas. What is the problem here? We are in a situation where we have a very small volume, very small space available. So this is a huge constraint. The second constraint is that we have to use a liquid fuel. But a liquid fuel must be in the zone where you will ignite the mixture fuel air. It must be gaseous. So this will give us a huge constraint, and when you combine these two constraints, you are even in a more delicate situation. So you need to use a liquid fuel that must be gaseous before combustion mixed with the air, and you need to do that in a small volume, a small length. So it's not only a small volume, it's a small length and a small, let's say, radius or radial distance available. Another constraint is the fact that you cannot use the igniter during the flight. So the igniter is using too much energy for the engine, and in normal conditions, in most conditions, in fact, the igniter will not work. So there is no igniter that is active. So that means you have to work with an auto-ignition of the system, and you need to find a solution so that if you have a problem, that you will be able to reignite the engine, restart the engine, reignite the mixture. This is certainly another huge constraint. What is also a big problem we will have, this is with the performance. I will discuss today the performance, and there is a performance that is extremely often totally neglected in courses related to combustion, but that is extremely important for gas turbine engines. These are the pressure losses. So the parameter that we have called lambda cc, which is equal to PT2 at the entrance of the combustion chamber minus PT3 at the exit of the combustion chamber, divided by PT2, this is a parameter that is extremely important. Because don't forget, we have behind the turbine, and this turbine has not so much energy available and must drive the compressor and still have a lot of energy behind in order to deliver the thrust. So this parameter, the pressure losses, the total pressure losses in the combustion chamber will be a very fundamental parameter that we need to, let's say, optimize, so minimize the loss that you have in the combustion chamber. Okay? Of course, an extra problem you will have, this is the mass. This combustion chamber must be light. So very short, because you don't have a lot of length between the turbine and the compressor, very small in the radial direction, very light in everything, low lambda cc, and using this liquid fuel that must be vaporized before getting into combustion, and an igniter that is not running. I will, in this part of the course, in this component that we call the combustion chamber, not make really a difference between normal combustion chambers and afterburning chambers. Of course, the afterburning chambers are different, but a lot of what we will say is also applicable to the afterburning combustion chambers. And finally, there is a point, there are 2 points, let's say, that we need also to discuss in this course on combustion chambers. These are the emissions. We need to look at the emissions produced by the combustion chambers of gas turbine engines and aircraft engines in general, not only CO2 but also NOx, also the CO at low altitude, also the soot, also the H2O, the water vapor. Everything must be analyzed. And finally, we will need to discuss a problem that we have not at all discussed from the beginning. This is how we start this engine, because this is still a mystery of how are we starting such an engine from rotational speed equal to 0, from mass flow rate equal to 0, or are we getting this engine started on the ground, but also, as I indicated you, a huge danger. This is the blowout of the engine, extinguishing the flame, and you do not have the igniter that is working in cruise. So, or are you also restarting, restarting the engine in cruise at 10 kilometers, 11, 12 kilometers altitude? These are very specific problems that are very often totally neglected or totally not existing in other fields where combustion is important, but where you are not burning liquid fuels and where you don't have the same constraints and the same limits and the same very difficult working conditions that we have here. Another point, of course, that we need to discuss, this is the influence of the very much changing working conditions. Don't forget that this combustion chamber is working from sea level up to 12 kilometers, 13, 15 kilometers altitude. So with a much changing pressure at the entrance of the combustion chamber, and also a largely changing temperature of the air. Or are we, let's say, solving this problem of much varying working conditions of the combustion chamber with still the same requirements that this must be very low, that this, the combustion chamber efficiency must be very high in all these flight conditions. So in an aircraft engine, in an aero engine, we have very specific problems related to combustion chambers. I will also show you some elements, that hardware elements, some components that we have here available. So what is the problem at the beginning? So you have a situation where at the exit of the compressor, so this is the compressor exit, that you have a flow of m dot that is at PT2, at TT2, and that is at a speed V2 or a Mach number M2. What is the, let's say, it depends, of course, if you are speaking about axial speed, non-axial speed, so we can certainly discuss about that, but we will be with a speed that is very high. So let's say something like 150, maybe 200 meters per second. We will create a mixture of air and fuel, whatever this fuel is, gaseous or liquid, that is becoming gaseous, that is diesel, that is kerosene, that is another fuel, I don't know, hydrogen. But you will have, let's say for normal fuels like kerosene or diesel, you will have a flame speed that is very low. The flame speed will be at a speed like, if you take this as the speed of the air at the air of the exit of the compressor, the flame speed is a vector like this one. The speed of the flame will be a few, let's say between 1 and 10 maybe meters per second. So you see, you have a ratio, an order of magnitude between the flame speed that you will reach with this mixture and the speed of the air around. This is not acceptable. If you do something like this, you will blow out the flame directly. So the first thing that you will have to do, this is to create a divergent. So the combustion chamber starts with a diverging channel, where you will largely increase the section A2, that is at the exit of the compressor, into a section that we can call A2 prime, if you want, that is much larger than A2, so that you are decreasing the speed. But you cannot decrease the speed down to, let's say, 5 meters per second or 10 meters per second. This is much too low. You would need a much too large increase of the section. You would need a 10 times increase at least of the section. Even if you are speaking in square, that means an increase of the section with a factor 3, with a factor 4. That would make the chamber much, much too large. It's not something that you can do. So what will they do? They will, in fact, create a second combustion chamber, if you want. This is what is called the liner, or that is called the flame tube. So we will create an inner tube, a second chamber inside the external one, let's say. So you have an inner tube and an outer tube. And there you will create what? Recirculation. So you will open this flame tube, let's call it like that, this inner tube that you have there, and through this inner tube you will inject a part of the air that is passing here inside. So the air will pass like this, and a part is coming here, and by creating this flow is flowing radially, is entering into contact with this one. A part will go in this direction, a part will go in this direction, and a part will go in this direction, a part will go in this direction. And what will you create? You see that you will create a vortex that is trapped, that is contained here inside, and a second vortex that you will have on the second half of the chamber. And like this, you create in this zone a kind of zero speed condition. Of course, what I'm discussing here is incomplete because I'm just discussing the air. I have not added the fuel in this, and the fuel you will add it in this way. So you will inject the fuel in this way, and that will be mixing, and we will see how it's working exactly with this air that is turning there in this recirculation zone. What you will have also, this is that there is air entering into this direction. This air that is entering into this direction will help mixing the flow and will also contribute to a fundamental aspect that we need to have in this combustion chamber. As we are using a liquid fuel, you need to atomize the fuel. And this air that is flowing, let's say coaxially, it's a